Hi, in this video, we're going to take a look at some of the factors that affect how your blood is flowing. So this relates to a topic called hemodynamics. So hemo means blood, dynamic means power. So as blood is traveling inside the blood vessels, they exert pressure onto the walls of the endothelial cells. So we could measure, for instance, our blood pressure easily. Now, if we take a look on this chart, diagram, here is pressure measured in millimeter of mercury. The x-axis shows you from different location of, for instance, the blood vasculature. For instance, from aorta to the major arteries all the way down. So for instance, you can see we could measure and see our systolic blood pressure when your heart is working the hardest, and when it relaxes, you can measure the diastolic blood pressure. Now, we say that our blood pressure really is determined by several factors. For instance, your cardiac output, so how hard your heart is working, as well as, for instance, the amount of blood volume is also related. And also the third factor is vascular resistance. So for instance, vascular resistance is one of the reasons that helps determine blood pressure. And for instance, it tells you resistance is about the friction that's occurred between your blood as well as the blood vessels. So for instance, it really depends a lot on, for instance, the size of the lumen of the blood vessels, for instance, arteries versus the veins versus those of the capillary. So the size of the lumen differs. If you have, for instance, a smaller lumen, okay, do you think it will have a higher resistance or lower resistance? Right, if you tend to have smaller lumen for the blood to travel, they actually have more resistance. It's harder for them to travel. And also, let's mention another one. Also depends on, for instance, length of your blood vessels. So, for instance, if you have a much, for instance, longer length of the blood vessels, would they have more resistance or less resistance? Right? If it's a longer one, it's harder to travel as well, so higher resistance. Okay, so now let's take a look at, for instance, to help pump blood back, for instance, from the veins, the venules, all the way back to the heart, we call it venous return. Now we said our veins are a little bit different, for instance, from the arteries. They have less elastic tissue to help um, with contraction of the blood vessels. So they need extra help. So for instance, we have our skeletal muscle pump. Each time when your muscles are moving, for instance, when you're exercising or moving, these muscles help push the blood back. Of course, some might go back a little bit, but with the valves, hopefully they will go in back or back all the way, eventually back to your heart. Now, also, respiratory pump is related to our muscle, very important for breathing, our diaphragm. So when we are inhaling as well as exhaling, inhalation and exhalation, our diaphragm, for instance, is moving as a result, and that will help push some of the blood back from the veins all the way back to the heart as well. Now let's take a look at what else would regulate your blood pressure. So we have those that are undergoing through nervous regulation, we call it the neuroregulation, versus those that are regulated by hormones. So for instance, under the neuroregulation, we have baroreceptors. These are the ones, the receptors that are going to detect changes in your blood pressure. We'll take a look at where they are. Now we also have chemoreceptors. These are receptors that will detect changes in, for instance, concentration of oxygen, concentration of protons, etc. Yeah. So let's take a look at where some of the regulation center is. So one very important thing is after, for instance, our baroreceptor, which monitor blood pressure, okay, as well as our chemoreceptors, after they monitor, for instance, the chemical changes like proton concentration, CO2, oxygen, they send their messages to the cardiovascular center. So it's right here in this region. Do you remember which part of the nervous system this was with? Right, was it the pons or was it the medulla? Right, it actually is. It's not the pons. Pons is right here, so it's in the medulla oblongata. Okay. So it's in the medulla oblongata that we have our cardiovascular center. So they receive messages from the receptors and they will process what's going on and they will send out, for instance, the effector through, for instance, remember your vagus nerve that leave the regions of the head and it goes all the way to the heart. So if it's traveling through the vagus nerve, this is our parasympathetic nervous system. It tells your heart to decrease how much they're working and relaxes more. Okay? Now, if it's going through sympathetic nervous pathways, for instance, it tells your heart to work harder. For instance, it's going to pump harder, contract harder, as well as tell your blood vessels to constrict, so to get ready for fight or flight. Now let's take a look at where your baroreceptors are. So they are located, for instance, very, very close in this region. So if you take a look at the arc of aorta, we have our baroreceptor right here. Another one is located in the carotid sinus. So they are the ones sending the messages to your cardiovascular center in the medulla oblongata. And the red nerves, for instance, neurons, are the ones sending messages back to the heart, either to tell it to pump harder or to relax. Now, also, this works if we have hormones that help us regulate it. So we have, remember, our RAS system. This is our renin, angiotensin, and what does the other A stands for? Aldosterone, right, system. So now don't forget, we'll take a look at this in the next slide. Now epinephrine as well as norepinephrine, they also work to help your heart contract much faster, increase your heart rate, as well as by giving it more calcium supply, for instance. Now also our antidiuretic hormone, remember ADH, our vasopressin. So all three of these work when, for instance, you have a drop in blood volume. For instance, if it's severe dehydration or blood loss or related to ions concentration, this leads to also a drop in blood pressure. Okay, when your volume drops, pressure also drops. So all three of these will try to compensate, for instance, to increase the fluid in, for instance, in your system, trying to bring up your blood volume. As a result, your blood pressure will come back. Now, what's different from them is atrial natriuretic peptide. This is a hormone synthesized from the atria of the heart. Okay. So it works differently from the other three on the top. So this works when you have high blood pressure and you want to lower it. So when your blood volume is high, resulting in higher blood pressure, atrial natriuretic peptide, this will be secreted to help, for instance, lower the blood volume as well as drop a little bit of your blood pressure. So they do so by, for instance, increasing the loss of salt as well as water in the system. So let's take a look. As a refresher, your renin, angiotensin, as well as aldosterone system. So this is in response to when you have dehydration, sodium ion deficiency, or you lost a lot of blood through hemorrhage. So it causes a drop in the volume in your system, and that relates to a drop in the pressure as well. So in our kidney, we have this very special cell. We'll take a look at them when we get to the renal system. So they secrete an enzyme called renin, and renin will work on angiotensinogen and break it into more active form, but this angiotensin 1 still has to be activated again to become the more powerful one. So angiotensin 2 works on your, for instance, adrenal cortex, tell them to make more aldosterone. So remember, aldosterones are the one to help you reabsorb sodium ions. And as you keep your sodium ions, water is going to follow. So you have more water, retainment of water. So as a result, blood volume increases. Okay. Now the other side of this is constriction of your arterioles, and that also helps bring back your blood pressure. Okay. So the focus here is, don't worry too much about the detail here. We have seen it in chapter 18, but focus on what causes it and what it's trying to um, counteract with. Now let's take a look over here is a table. Okay, so this is just to show you how some of those hormones act. For instance, norepinephrine, epinephrine, and you will see that a lot of them, like ADH, norepinephrine, so they are trying to increase your heart rate, make sure it's pumping harder, make sure your vasculature is tightened up. Okay, so but you will see that AMP, which is atrial natriuretic peptide, works oppositely from them. Now, so we have a way, our body has a way to auto-regulate themselves. So auto-regulation means our body has ability or tissue to adjust, for instance, blood flow depending on the situation. Okay, so it depends on changes in the physical environment. So sometimes if it's too warm, like a very hot sunny day, for instance, your muscles will be relaxed. So as a result, when your muscle relaxes, the smooth muscle relaxes in your blood vasculature, it helps vasodilation. Okay. So if it's a very cold climate or cold environment, the opposite occur, right? Your muscles are going to tense up and causes vasoconstriction. Okay. Now, chemical changes also depends on, for instance, our chemical that are released, local hormones that are released in our tissue. Now, NO doesn't mean no, it means nitric oxide. So this is a very, very powerful vasodilator. So what it does is when it's synthesized by the cells, for instance, a lot of times our endothelial cells will secrete them. And so if this is the lumen of your blood vessel, after nitric oxide is released, now it will dilate the blood vessel's lumen. So the lumen will become more dilated while I'm exaggerating it, yeah? But what do you think will happen to the amount of blood in here? Would you have more blood flowing or less blood flowing through? Right, when your diameter is wider, you have more blood flow. Okay? So as a result, okay? So this is very important to help us with increasing of blood flow to regions, and nitric oxide is, for instance, readily degraded after it's done its job. Okay, this is the end of the first part, and we'll see you in the next video lecture.